throw a lightning bolt at something? Well, as it turns out, it's technically quite possible to do. Today we're going to fire this directed energy device that I built a while back. I call it the Lorentz cannon. The cannon is supported by a 240,000 volt pulse forming tower called a Marksbank, which delivers an electrical power pulse of several gigawatts to the 30-barrel armature gun mounted on top. The gun then initiates a plasma channel through the air at current levels found in natural lightning and can direct this plasma channel towards any grounded target. Now you might be wondering, why would anyone build such a thing? Well, back in the day when I lived at survival research labs, my task was to make electrical devices that could somehow interact with the machines. But these machines were often quite violent and unpredictable, and they were usually loaded with weapons and explosives. So how could you arm an electrical device to survive in such a hostile environment? The answer? Use pulsed power. And if that doesn't work, use more pulsed power. Now, capacitor banks are a cheap and cheerful way to blast objects with hundreds of megawatts, or shower large areas of machines with molten metal. But to blast an object with capacitors usually involves running very heavy cables, and dragging these heavy cables up to a fast and mobile machine wouldn't be very practical at all. So I wondered, could you somehow direct a lightning bolt at a hostile machine instead? I'd read about lightning researchers who could direct lightning bolts to the ground by firing rockets trailing a thin wire. But how can a hair-thin wire possibly carry tens of thousands of amps? This is where the Lorentz force comes to the rescue. When you pass current through a wire, a magnetic field forms around it. Lorentz found that this field produces a force that compresses the conductor, which increases with the square of the current. Now normally, if you tried to pass 10,000 amps through a thin wire, it would instantly vaporize. But if the current rises fast enough, the Lorentz force grows faster than the explosive force, and it contains the hot plasma into a super dense channel. It's a great trick, but there's a catch. In order to get the current to rise that fast, you need to hit it with a rather large voltage pulse, and a fast one to boot. Now this is easy for a storm cloud to do, since it has hundreds of millions of volts available. But I wondered, could mere mortals pull off such a feat? As luck would have it, SRL had recently rescued a bunch of 20,000 volt capacitors from the scrapyard. But some quick calculations revealed that we needed over 120,000 volts to produce a fast enough edge. So to get 120,000 volts out of 20,000 volt caps, I borrowed the Marksbank approach used to target, then start charging the Marksbank. The top scale on this high voltage divider is calibrated to show the final output voltage. 150,000 volts is right about here. Okay, the bank is charged and ready to fire. 3, 2, 1. Ah, that familiar shockwave. I just hope the neighbors aren't too upset. Looks like I need to adjust the aim compensator upwards a bit.